I'm Sandeep Chaudhary, professor at the Department of Civil Engineering, Indian Institute of Technology, Indore. In my capacity as course coordinator, I would like to welcome all the participants for the 5-day development program on sustainable construction technology from today, that is July 26th to July 30th. We'll keep the introduction very brief because we have formal inauguration at 11 a.m. by the AICT for all the courses being funded and coordinated by AICT. Sustainability, as the name in the title, has been globally recognized as an integral development goal for all development programs. Sustainable construction technologies focus on improving the performance of structures while reducing the overall cost and environmental impact of the construction. In order to foster the field application of sustainable construction technology, the Department of Civil Engineering, IIT Indore, sponsored by AICT, has organized this faculty development program. And during the course of next 5 days, we'll cover environmental challenges associated with construction industries, their management using sustainable construction technologies like use of alternative raw materials, construction using indigenous products, reduction of wastage, and efficient building planning design. So we'll formally begin with the very first lecture, that is the introduction to sustainable construction technology. Sanchit, I hope I'm audible and my screen is visible. If there's any issue, please let me know in between. You can put a message to me also on mail or on WhatsApp. Okay, yes, so Sanchit, can we formally begin? Okay, so if there's any issue, just let me know. Okay.
Sir, I think we lost your audio.
Yeah, no, I am there. I'm just trying to actually this toolbar. I'm trying to drag it out. I'm not able to do it. Anyway. Okay, so if we talk about this very concept of sustainable construction technology, let's first talk about construction. And construction, being an integral part of the development of our society, has greatly changed the surrounding we observe. But this construction, of course, comes at a great price. Great price in the sense that we often feel the shortage of the sand, and those who have been working in this domain and those who have been going through the newspapers or other medias, you will realize or you will recognize that there are a lot of news where there's a lot of talk about this sand shortage. And in fact, our National Green Tribunal has banned this mining of sand at many places. And there was a time last few years when in many states the construction activity was stalled completely because they were not able to mine the sand because of the environmental concerns, and they did not have an alternative. Of course, now people have come with alternatives to that. We'll be discussing that. One of the speakers will be discussing about that also. It also leads to air pollution and of course a lot of waste generation. So these are some of the issues which we know, but however, we also know that the construction has to go on. So we need to find out via media, or we need to find out some solution where there can be a tapering of the construction as well as this requirement of raw material, etc. So we talk about the future of engineering, particularly this construction engineering. We can say that the construction is an integral part of development. However, it is also causing damage to the environment. And this constructed space and natural environment, they need to coexist. And the solution is simple. We have to incorporate sustainability in the construction. Now, how do we define the sustainability? We often talk a lot about sustainability, and now it has become a sort of keyword, and people keep on talking a lot about this sustainability. But from our perspective, how do we define sustainability? We can define it as the ability of maintaining a certain rate of level. That is, whatever we are doing today, say, whatever construction we are doing today, can we keep on doing that construction for the ages without any problem? In case if we feel that no, that's not a sustainable solution, or after 20 years we'll not be able to keep that level of construction, that means the solution is not sustainable, and there are certain sustainability aspects which need to be addressed. In application, it refers to any activity that is not limited by or that does not cause damage to either of the following: society, environment, and economy. And that's also very tricky, because normally we, as academicians, we work in one of the domains. Some of us work in the domain of environment, some of us work in the domain of society, some of us work in the domain of economy. So whenever there is a talk about sustainability, we look from our own aspect. If I'm an environmentalist, I look from the environment aspect only. If I'm an economist, I look from economy aspect only. And if I work in the area of society, I will look from that aspect. But we have to keep a delicate balance between all these three pillars: environment, society, and economy. Only then we can achieve this sustainability. Now, how do we define the construction practices then? So any activity which is tangible or non-tangible and which contributes in bringing the constructed structure in its finished form can be referred as construction practice. Now, this construction practice, they can be broadly classified as planning and designing. That's also one of the construction activity. Then pre-construction, construction, and operation and maintenance. Now, so if we define types of construction practice, so based on their impact, construction practices can be classified in the following way. You can see a right-hand side diagram. Now, some of the construction practices might be economic from the nature. Some of the construction practices might be addressing social aspects principally or primarily. Some of the construction practices might be addressing eco-friendly, or you can say environmental concerns primarily. We don't need such activities, construction activities, which are just looking for the economic aspect, or which are just looking for the social aspect, or which are just looking for the environmental aspect. We need to see those construction practices. We need to look for those construction practices which take care of all of those. Say if there is certain construction activities is just talking about economic aspect and social aspect, at the most you can tell that construction activity, or you can define that construction activity as equitable construction activity. If there's some construction activity which is eco-friendly as well as which is looking for the social aspects, you can define that as bearable. If there's some construction activity which you can define as economic as well as environment friendly, you can say that is viable. But the sustainable construction activity will be that activity only which will take care of economic aspects, which will take care of social aspects, and which will take care of environmental aspects. So now there is no true parameter for quantifying these construction practices. That's the issue. Like mostly as engineers or as researchers or as academicians, we always look for quantified techniques where we can just put it in black and white, that either it is yes or it is no, and we can define, we can compare in terms of numbers, because we always look for numbers. But unfortunately, here there are no numbers to work upon, and there are no true parameters. It comes with the experience, and we need to look from many aspects. And these terminologies are relative and show the benefit of one practice over the other. Some practice might be considered economic by one person, but it might not be considered economic by other person. Some activity might be socially okay from one perspective, but not socially okay from other perspective. Some activity might be environment friendly from one perspective, but not be environment friendly from other perspective. So it depends on case to case also, but we have to come up with a solution.
ऐसी जगह तो है नहीं कि IIT है। अब आप यहाँ से करेंगे तो यहीं तक की इसकी वैल्यू है, इसके बाहर आप निकलेंगे कहाँ से किया तो फिर वो मामला गड़बड़ा जाएगा।
I think somebody is on. Sanchit, you need to mute. I don't know. So sustainable construction practices are activities that are better than their alternative options in all the parameters. Now they are balanced. Yeah, Sanchit.
Sir, please unmute yourself.
Sanchit?
Yes, sir.
It's okay?
Yes, sir.
I think there was some disturbance.
Yes, sir.
So sustainable construction practices are the activities that are better than their alternative options in all parameters. Now they are balanced and account for all social, economic, and environmental needs. Now, how do we define and how do we select the sustainable construction practice? That which practice we'll call as sustainable construction practice, which practice we'll call as non-sustainable construction practice. Now this is a relative assessment. And so there will be often disagreement over selection of sustainable construction practices, and no harm in that. As we discussed earlier, for some, economy may be of importance, while for others, environment may be important. Another example like can be a choice on low-cost housing in the outskirts of a city or high-cost housing within the city. Because here there is a choice in the society and economy. If you are going for low-cost housing in the outskirts, then you have to spend on the transportation that will have its own environmental concerns. If you are having a high cost housing within the city, it will have economic concerns. So considering the difference in opinion, selecting a suitable sustainable approach is possible through a common consensus only. Okay, so there can be often disagreement or selection of sustainable practices. Now, the only way to reach for sustainable construction practice or to define some practice as sustainable construction practices to arrive at a common consensus. Now, how do we arrive at a common consensus? Because each of us has a knowledge of a different domain. One of us might be expert of economics. One of us might be expert of environment. One of us might be expert of social aspects. And it's not only about expertise. We tend to have our natural inclination towards certain aspects. So we need to come at a common platform and we need to develop our concern about the other aspects also. And that is one of the primary reasons for organizing such courses, where all of us can come together on a same platform and we can develop a minimum common understanding that yes, this type of practice will call a sustainable construction practice. Now, so sustainability requires consensus on all three of its pillars. That is economy, that is how to share the economic burden. Society, what is actually beneficial for the society. Environment, to which extent the damage is acceptable. As an economist, I cannot say I will just look for economy. As a social scientist, I cannot say I will just look for society. As an environmentalist, I cannot say that I will just look for the environmental aspects. Now, how do we reach this consensus? One way is like sitting together, like we are today sitting together, discussing together. But when we talk at a broader perspective, like the size of our country, the population, then it can be possible through the relevant governing agencies also. And that's where the role of governing agencies become very important to arrive at that common consensus, to provide some data lines, to provide some baselines. Now, this role of governing agency can simply be highlighted by comparing India with Vietnam. Let's talk about fly ash. All of us know that fly ash was a big nuisance about 2 decades back, and then now today, more or less, we have settled that issue. So in India, actually, it became a widely accepted industrial byproduct after its use was initiated in 1994. Now, the same fly ash, its utilization was introduced in Vietnam in 2014. That means for 20 years, they were struggling on using this fly ash properly just because of this late activity of governing agencies. So in India, in our country, the governing agencies became alert as long as back as 1994, and since then, more or less, we are able to control that fly ash nuisance. Also in India, many agencies are actively involved in bringing sustainability in construction practices. And through their expertise, they have formed several guidelines for providing consensus on sustainability. Our speakers will be talking about certain guidelines like Griha rating and some other guidelines, Indian Standard Code guidelines, and all other guidelines. And Bureau of Indian Standards has also published several documents, which of course serve as the basis for construction practices. How do we approach sustainability then? As researcher, as engineer? Now, this can be approached from different aspects in construction practices. We can look for use of green materials. We can look for sustainable structural elements. We can look for waste utilization. We can adopt latest technologies. We can improve long-term sustainability. We can go for efficient design and planning. And of course, nowadays, most talked about aspect life cycle assessment. Some time back, we were just talking about the cost of the construction. That is also in terms of money, in rupees or dollar, whatever. But now it's not about that cost, which is just in terms of rupees. We talk about the life cycle assessment. What is overall life cycle of a product? And in fact, that is converted to life cycle cost. What is life cycle cost of a product? What is life cycle cost of a structure? Where we convert the environmental impact in equivalent amount of money. And then we tend to see the overall life cycle cost. So a structure may be economic today, just in terms of money, but if we see its overall life cycle cost, then that structure might be costly after 20 years or 50 years for its entire life cycle. A simple example is like, say, if you are using steel structures, they may be costly today, but they are reusable. So maybe down the time, if you see overall life cycle cost, their overall life cycle cost may be less than the life cycle cost of reinforced concrete structure because they can be used multiple times. So that is just one of the examples. So the idea is we need to see from the overall perspective, not only what we are spending today, but down the line, overall life cycle in next 50 years, next 100 years, which structure is going to be costly for us, and why we are converting now environmental impacts in terms of money, because of course that is on anyway result that always results in terms of money only we have to spend then in another form. If today we are just saving or making some structures which are damaging the environment, tomorrow we have to spend them on again. And like today only, you might have seen the today's newspaper, the front headlines in all the newspapers are that in our river Ganga, now they have found these plastic wastes, microplastics. So in our holy river, even because of this use of plastic, which at that time people tend to think because it was cheaper, because like these plastic bags were cheaper than cloth bags and other alternatives. So people used it. But now our holy river that has been like polluted by because of that microplastics. Now the amount of money which we have to pump in making that clean is will be much bigger than whatever amount we have saved in use of plastic. So we'll be discussing about these different aspects briefly. Of course, the speakers will be discussing these aspects in detail. whenever they'll be taking lectures. We'll have some brief discussions. So one is use of green materials. So a simple and reliable approach towards sustainable construction practice is the use of green materials. And construction materials and building products that perform similar to conventional materials and have a smaller carbon footprints, they are called green materials. Like you can see a picture of bamboo-based construction. Some of the examples of green materials are use of blended cement, which reduces the clinker requirement and is beneficial for environment. Use of unfired bricks, which reduces carbon footprint and preserves clay. Use of natural products like bamboo, as you are seeing on the right hand side. And of course, the speakers will be discussing a lot about these green materials. Advantages are they are reliable and we do not need technical expertise as such because they mostly come under the quality check of the supplier and mostly they are cost beneficial. Let's see some of the locally available green materials. Like if we talk about southern coastal regions, we do have a lot of laterite mud, clay, and red mud. They can be used to prepare materials like clay tiles, laterite blocks, glazed tiles, and laterite stone. Also, the southern states have large deposits of granite, limestone, and slate, which are ideal for building structures. Central India is abundant in clay, red mud, granite, marble, sandstone, which have been used in construction of a wide variety of structures. Bamboo also has found a wide range of construction applications. Then arecanut trunks, coconut palm trunk, bamboo, thatch using coconut leaves, pine wood, rubber wood, all are popular in various parts of the Karnataka. Coming to other important aspect is waste utilization. So what is all this? So waste utilization refers to the reusing and recycling of waste into useful products. And we know that construction is a high volume work, so it significantly affects resource consumption. And we can replace these conventional resources with waste. So what we can do is through this, we can easily dispose of waste and we can reduce pressure on conventional resources. Examples are like we can use waste glass, recycled aggregate, recycled PET waste. We'll see many such examples in the coming slides. So we have twin advantage here. One is we are able to dispose the waste, which otherwise we need to spend money, we need land to dispose them of, or if we are burning them, then there is a lot of pollution. So one first advantage is we are able to dispose that waste properly. And this is of course better than landfill disposal or incineration. If we are using landfill disposal, we have to just waste a lot of land. If we are going for incineration, it has its own environmental concern, as well as it is leading to natural resource preservation. So by providing an alternative to conventional materials, waste reduces the requirements of natural resources, and it also reduces the pressure on their extraction. How can we use like the waste and what are its possible applications, particularly in the field of construction? So typically the waste can be used as supplementary cementitious material, that is as a replacement of cement or as a partial replacement of cement. We can use them as a replacement of natural aggregate also. We can use them as reinforcing material also. We can use them as architectural material also. Let's see some of these waste which have been conventionally used in our country or in other countries. Any material, then the size should be more or less the same, or at least the size of the supplementary cementitious material should be smaller than the cement particles. Only then we'll have sufficient surface area for the reactions to take place. So fly ash, we know composition and properties, they depend on the type of coal or biofuel burned. Class F fly ash, it contains less than 7% lime, glassy silica and alumina. Of course, we know that cement typically comprises of this calcium silicates, calcium and silica. So if you are looking for some alternative cementitious material, then it needs to have some lime and some silica. Only then it can replace the cement. So the class F fly ash contains less than 7% lime, then glassy silica and alumina, and it requires a cementing agent, of course, like Portland cement, quicklime, or hydrated lime to react and produce cementitious compounds. Class S contains more than 20% lime and it's self-cementing. Applications are pozzolana Portland cement. Those who are working in this area for last more than 2 to 3 decades, we know that there was a time when we used to get only ordinary Portland cement in the market, and slowly that ordinary Portland cement has been wiped off from the market, and we just get pozzolana Portland cement, because this pozzolana is nothing but fly ash which is there in the Portland cement. Of course, pozzolanic material is that material which, when that comes in contact with water, it forms cementitious properties. So the now fly ash has found a large application in Portland pozzolana cement, and now it has become almost mandatory for the cement companies to use the fly ash in this cement manufacturing. There was a time, of course, when we used to work on this fly ash, then the thermal power plants, they used to send the fly ash up to the doorsteps of the laboratory or of the institute free of cost. They used to cover up the expenses for the transportation also, but once the cement companies have started using, now it has become even difficult to get the fly ash from thermal power plants. So that is the role of governing agencies which has come in picture. And then they are used in embankment, soil stabilization, flowable fill, asphalt concrete, geopolymers, of course, which is coming up now rapidly as a replacement of normal concrete, and roller compacted concrete, fly ash bricks, etc. And this is a microstructure of coal-based fly ash. The particles are more or less spherical, which are ideal particles from our perspective, because they will cause greater, they will provide us greater surface area for the reaction, like in soil stabilization, in fly ash bricks, etc. Another important supplementary cementitious material is GGBS. It is obtained by quenching molten iron slag from a blast furnace in water or steam to produce a glassy granular product that is then dried and ground into fine powder. The main components are calcium oxide, silica oxide, Al2O3, and MgO. And of course, again, we are seeing, because we are using it as a supplementary cementitious material, so of course it should have a large amount of calcium oxide and silica oxide. And if you increase the CO content, it raises slag basicity and increases this compressive strength. The benefits of using GGBS are: it reduces the risk of damage caused by alkali-silica reaction, high resistance to chloride ingress, and provides high resistance to attacks by sulfate and other chemicals. And this is typical production. Basically, it is we get it from the steel industries, and this is the microstructure you are seeing on the right hand side, though the particles are not as spherical as fly ash. So that's why fly ash has a greater advantage, added edge over the GGBS. Another supplementary cementitious material is rice husk ash. It's an agricultural byproduct which is obtained by burning husk under controlled or uncontrolled temperature. It's highly pozzolanic because it contains 85% to 90% amorphous silica. Now, please see the word very carefully. Often we think that only the presence of silica is important, and if there's silica, then the material will be pozzolanic. But we should understand it's about the manner in which it is present. The silica can be present either in or the form in which it is present. Silica can be present in amorphous form, or silica can be present in the crystalline form. So essentially, the amorphous form is only of advantage to us. So we have 85% to 90% amorphous silica here in rice husk ash. So that's why it's highly pozzolanic, and it is also about 5% alumina. It is a very large surface area resulting from microporous structure of ash particles. It has a wide range of applications as filler, additive, abrasive agent, oil adsorbent, sweeping component, etc. Again, the benefits are more or less similar. It reduces the risk of damage caused by alkali-silica reaction, high resistance to chloride ingress, provides high resistance to attacks by sulfate and other chemicals. And we can have this fly ash in ground form or unground form. So you can see the microstructure. Of course, when we ground it, we'll see the finer particles. And nowadays, actually, this rice husk ash is available in form of bags, like we get the bags of cement. So similarly, we can procure the bags of silica, this rice husk ash also. Another important and interesting supplementary cementitious material is silica fume. It's ultra fine powder which is collected as a byproduct of silicon and ferrosilicon alloy production. And it has spherical particles which are less than 1 micrometer in diameter. And its high fineness, it's quite fine. It's approximately 100 times smaller than average cement particle. Therefore, its high fineness and the presence of SiO2 between 85 to 98.5% is responsible for highly pozzolanic reactivity. And the oxides of silica fume, they react with and consume calcium hydroxide, that is CH obtained from hydration of cement. Benefits are there's a densification of matrix, strength improvement, decrease in porosity, better resistance to chemical attack. And you can see the microstructure, so spherical particles. And often it happens that if you have to go for very high strength concrete, then we need to go for silica fume. We need to incorporate silica fume. In fact, if you see the recent changes in Indian Standard Code, also Indian Standard Code on mixed design, then when they define the high strength concrete, or they define the mixed design of high strength concrete, so there it is suggested to use silica fume. And in fact, in the example which they have put in their code, they have considered silica fume in their own example. So essentially, if you are going for very high strength concrete, you need to look for this alternative. Another upcoming supplementary cementitious material is metakaolin, and it is produced by calcination of high purity kaolinite clay mineral at a temperature range of about 700 to 850 degrees centigrade. It is finer than cement particles and helps to fill the micropores of the binder. It contains high amount of reactive silica and alumina. It provides better particle packing and a greater pozzolanic reaction rate. Benefits are it improves the compressive strength at early ages, and there's low permeability. It leads to low permeability. We know that if there's one parameter which defines the durability of the structure, like the compressive strength defines the strength of the structure, then that parameter is permeability. So if it is decreasing the permeability, then that gives a confidence that yes, it will improve the overall durability of the structure or overall durability of the concrete. And it also decreases the chloride ion penetration, again, which is a concern from the durability point of view. So this is a typical microstructure of metakaolin, more or less spherical particles. Another supplementary cementitious material is glass powder, and it's highly fine, and its further increases fineness, increases the pozzolanic properties. There's high amount of amorphous silica and high specific surface area, which accounts for pozzolanic reaction. It has less water absorption and smooth surface, which reduces water and admixture demand. Mostly when we are talking about supplementary materials, mostly it so happens that they have high water absorption, and which compels us to go for higher water cement ratio, or which compels us to go for the use of admixtures. But here in this glass powder, the advantage is, even though it's a supplementary material, or rather supplementary cementitious material, even then we just need less water, less water. Alkali silica reaction, of course, occurs among the silica of glass and alkali in cement, which leads to expansion, internal stress, and crack formation with disruptive effect. Thus, use of high proportions of glass particles is limited. Benefits are it improves the workability, mechanical properties, decreases permeability, improves the resistance to chloride ion penetration. Another important material is marble powder. It's basically an inert or quasi-inert material. And calcite and Portland cement paste lead to calcium carbon aluminates, which are formed by reaction between hydrated calcium aluminates and carbonated ions. Calcareous filler has an important binding properties that is developed by hydration of calcite and C3A. And people have observed strength improvement at lower replacements because of the filler effect essentially. And of course, if we go for higher replacement level, then they cause delay in setting time and lower the strength. Benefits are if we are going for a particular replacement level within certain range, it increases the compressive strength, it increases the abrasion resistance, and of course, sodium sulfate resistance. And you can see the problem with the marble stone dust is like the marble industry, which is they are facing is they have mountains of now this marble stone dust, and they're not still able to find out some permanent solution or some solution which can use this marble stone dust in huge quantity. The advantage with the construction industry is if we are able to establish the uses of some material, then we can use or we can wipe off that waste very quickly, because the construction industry is a huge industry. Now, people have worked on the different aspects in the research domain, and they have come up with different solutions like use of this marble powder in blades of steel, these wind turbines, and some other aspects in tooth filling and other aspects. But the idea is we need to look for from a bigger perspective, and until unless we are able to consume such waste in the construction industry, then it's difficult to dispose of such waste. So that's why for every waste, though people might have 5-10 different alternatives, but the only alternative which, as on today, which we can see when the waste is in a huge quantity, is the construction industry, because that is the only industry where we can dispose or we can utilize the waste in large quantity. So this is microstructure on the right hand side. So we can use the waste as aggregate also. Please read this as aggregate. And in the aggregate, we can use scrap tire rubber particles, waste plastic aggregates, construction and demolition waste, copper slag, marble quota slurry, or cenospheres. Of course, in the lecture by Dr. Trilok Gupta, he will be discussing about the utilization of these rubber particles and plastic aggregates, etc. So we'll cover just in brief that scrap tire rubber particles. Again, we know that this tire industry is there's a lot of tires which are discarded every year, and the interesting aspect with this disposal of waste tire is that it's a global problem. Mostly if we talk about waste, like particularly mining waste or some other type of waste, they might be localized in certain countries or certain cities or certain geographical locations. But this is a global problem to dispose of waste rubber tires. So what people do conventionally is they incinerate or they burn the waste rubber tire, and then they take out the oil and some steel fibers in that and make carbon blacks, etc. But it's a global problem, and that's not environment friendly solution. So we need to look for some other aspects. So these scrap tire rubber particles can be used, and they can be classified in 3 categories as chipped, crumb, and ground rubber. And they are obtained basically by mechanical grinding. And these rubber particles, they have low modulus of elasticity and flexibility, which enhances toughness and ductility of material. Also, they are low weight, so they provide lightweight aggregate cementitious materials. And they have a hydrophobic nature, which restricts the ingress of water and other solutions affecting the property of cementitious material. So huge dumps of scrap tires, and they can be used as ground, crumb, or chipped rubber aggregate in different forms in our construction. Another problem with, as I was discussing, is this plastic waste aggregate, and source of plastic aggregate is waste plastic bags, PET bottles, PVC pipes, high density polythene, thermosetting plastics, mixed plastic waste, and all of them can be used as aggregate, filler, or fiber in preparation of cement, concrete after mechanical treatment. Advantage is they are strong, lightweight, and durable composite. They reduce the weight density of the product. They increase toughness, flexural strength, abrasion resistance, increase chemical durability, shrinkage resistance. Of course, there's adverse effect on the compressive strength because this sort of form impermeable layer in the concrete matrix. So that issue needs to be sorted out, and so we can use them up to certain replacement level. And these are waste plastic aggregate concrete and the manner in which we can shred them. Dr. Trilok will be discussing in detail about this. We can use also C&D waste. Like C&D waste includes building materials such as insulation, nails, electric wiring, shingles, and roofing, as well as waste originating from site preparation such as dredging materials, tree stumps, and rubbles. And demolition waste is the waste debris from destruction of building, road, bridges, or other structures. We can use them in construction materials, like we can make recycled coarse aggregate, where we can recover coarse aggregates from demolished concrete, having enough ability to produce good quality concrete. We can also use construction debris as fine aggregates. Of course, there is a small effort which is required for processing construction debris as fine aggregate. And it has applications in manufacturing of unfired bricks, mortars, paver blocks. There are professional agencies and companies which are working in this area. Like in Kolkata, there's a company. In Surat, the Surat Municipal Corporation is working on this. In Indore also, Indore Municipal Corporation is also working on this aspect. And so they can be used in embankment material for improving soil bearing capacity. And if there is a ceramic waste in that CND waste, we can use them as fine aggregate. We can use recycled timber also, and wood can be reused, repurposed, recycled, or burned as bioenergy. And we can use them in pathways, coverings, mulches, compost, animal bedding, or particle board. So there's different types of waste. Normally we think that in the CND waste only we'll have some concrete portion only and we have to use, but there are different waste, like there's brick masonry waste also, ceramic waste also, concrete waste also, timber waste also. In fact, we need to be quite vigilant in this aspect. Like if we demolish certain structures, we still have a tendency, like if there are some glass panes or some glasses, we just break the glasses or throw them away. And we do know that the highest glass manufacturing, or the country which is producing the best, manufacturing the best quality of the glass is Belgium. But even in the Belgium, they are reusing the glasses, and it is not allowed to throw the glass. So the country which has so much amount of glass itself is not allowing throwing the glass, and it is suggesting the reuse, whereas we often tend to throw glass. And again, in the certain countries now, they have achieved such a level of expertise in recycling of CND waste that they have recycled the entire CND waste which they are getting day to day, and they're now digging out the land and taking out the CND waste which they have dumped in the ground, and they're taking that out and they're now recycling that waste. So maybe slowly down the line we'll also reach to that level. Another another waste which can be used as aggregate is copper slag. So it's an industrial byproduct which is obtained during the metal smelting and refining of copper. Texture is black colored glass, and it contains silica oxide plus alumina oxide plus Fe2O3. And it has showed certain pozzolanic property. And it has been found that if you use it as fine aggregate, it increases compressive and tensile strength of concrete, decreases water absorption and depth of carbon penetration. So you can see huge dumps of copper slag, and is the typical microstructure of copper slag. Xenospheres also have been used. They are produced as a byproduct of coal combustion at thermal power plants. So they are hollow microspheres of size 5 to 500 micrometer, having a shell thickness of 5 to 10% of diameter. They contain about 50 to 65% of amorphous SiO2. Again, amorphous, not crystalline. 20 to 30% Al2O3 and 1 to 8% of Fe2O3. And the inclusion of course, they have certain calcium, magnesium, phosphates, chlorides, and sulfates. They're lightweight, inert, and hollow spheres, and they have resistance to thermal and electric conductivity and superior acoustic properties. They're beneficial for developing lightweight cement composites. And ultra lightweight cement-based composites can be achieved by using them with density in range of 1120 to 1920 kg per meter cube, which otherwise is mostly 2400 to 2500 kg per meter cube. And this is the typical microstructure. Again, you can see very beautiful, very spherical particles. So once the particles are spherical, it's very much clear that they're beneficial for us. We can also use the waste as a reinforcing material, not the conventional, you can say, not replacing the steel reinforcement bars, but as additional reinforcing material, which at least can prevent the cracks, etc. So we can use scrap tire rubber fibers, recycled steel fibers, waste plastic fibers, recycled glass, carbon fibers, natural fibers. There's always a confusion when we are using these fibers in the structures or in the concrete. We often tend to think that when we'll be using these fibers, they will be essentially increasing the flexural strength of the concrete. But that's not quite true. Here, instead of going for improvement on the flexural strength of the concrete, mostly our prime concern is to arrest the cracks, at least minor cracks, because it is very well understood that there's still a lot of expertise, a lot of research is needed in utilization of these fibers when they will be able to completely replace the conventional steel reinforcement bars. So scrap tire rubber fibers, so we can use chipped or crumb tire rubber particles in fiber shape. They have flexible nature. They increase the shrinkage resistance in the sense that they will arrest the shrinkage cracks. And there's a better post-failure performance as fiber particles help to bridge the cracks. They increase the flexural strength and provide a high impact resistance. And of course, high resistance to abrasion because they will keep the surface intact. Chloride ion, higher chloride ion and chloride penetration. They're less affected by acid attack, measured in terms of mass loss and compressive strength loss. So these are scrap, like this is the microstructure of scrap tire fibers, and this is the photograph of rubber fibers, which we some time back used in our own laboratory, about which Dr. Trilok will be discussing in detail. We can also use recycled steel fibers. So a scrap tire consists of around 60% rubber and 20% steel fibers, and remaining 20% textile fibers. Of course, the processes are available for extraction of steel fibers by shredding, cryogenic process, pyrolysis process, or microwave-induced pyrolysis. So the tensile strength, modulus of elasticity, and specific gravity of recycled steel fibers are like that of synthetic steel fibers. And the improved properties of different composites due to incorporating these synthetic steel fibers could also be obtained by reinforcing recycled steel fibers. This provides an economic solution over the expensive synthetic steel fibers. So these are the recycled steel fibers. On the right hand side, you can see the microstructure. You can also use the waste plastic as plastic fibers. And the sources are waste plastic bags, PET bottles. PET bottles can be used as a reinforcing bars to structural members, but to a limited extent, not exactly a replacement of the conventional reinforcement. They are lightweight, high strength ratio, durable. They increase the flexural strength and impact resistance. And they also increase the abrasion resistance and shrinkage resistance, of course, because this is sort of binding property within the matrix because of these fibers. So that helps us in attaining that increased resistance. So these are typical photographs of waste plastic fibers, and you can see, of course, there are certain problems associated, like there's a sort of coagulation, and they tend to flock together, these plastic fibers, and we need to look for certain solutions where we can avoid this flocking or this coagulation of these plastic fibers. Of course, there are techniques available for that. And on this figure, you are seeing waste PET bottle is being used as reinforcement, of course, to a limited extent, like in say boundary walls or in certain slabs of limited span, not exactly for large spans and for where there are large moments exactly where there we cannot use it as a replacement of steel reinforcement. And of course, nowadays people are talking about this recycled glass carbon fiber reinforced polymer fibers, and they have high compressive, tensile, flexural, and impact strength. And use of virgin glass or carbon fibers, of course, is expensive, but still there's a lot of unfinished material which is left as waste. And along with this, there's a large amount of FRP which is discarded at the end of service life. So this discarded FRP or this unfinished material which is left as waste, they can be used as a replacement or as an addition to the reinforcing resistance or addition to the flexural resistance of the members. And if we are able to effectively recover the glass or carbon fibers from waste FRP, then they can provide similar properties as that of virgin fibers. And it has been observed that when these recycled glass or carbon fibers, they were incorporated in this concrete matrix, they improved, or in the mortar matrix, they improved the mechanical properties of the cementitious material. So these are photographs of recycled glass fiber. On right hand side, the photograph has been shown with the the scale just to have an idea of the size of the recycled glass GFRP fibers. And so they can be used in different shapes and sizes. Again, we can use certain natural fibers also, such as coir or coconut fibers, oil or date palm fibers, sisal fibers, banana tree fibers, bamboo fibers, which are available abundantly in the environment. And use of natural fibers, of course, increases mechanical performance of cementitious materials similar to that conventional fibers. They're lightweight, they're strong, they have a high strength ratio, and more or less they need no or very less treatment cost depending on the source of fiber. And of course, they are economically feasible over synthetic fibers. So there's a win-win situation that we have a lot of such fibers in abundance, and this is economically feasible solution also. And more or less, we are getting good strength also. So why not to go for such type of alternatives? And like here on the right hand side, left side, you are seeing coir or coconut fibers. In the middle figure, you are seeing sisal fibers. On the right hand side, you can see oil palm fibers. Of course, these are typical examples in our own localized geographical regions, in our cities, in our villages. We can have different types of natural fibers, and we can work upon them, and we can use them. We can try to see their applications. Now, having said that, actually, when we use, this is one of the ways like using the waste materials in sort of a construction material as a replacement or addition in cementitious materials or as addition in sort of concrete. But then we need to convert that to some structural element also, because somehow if we are able to convert this technology, or we are able to take up this technology to the next level, that we are directly providing some sustainable structural elements to the society, to the industry, then that can be a better solution, in the sense that one does not have to do all this R&D which we are discussing, and because there are a lot of like replacement ratio and all other things which one has to optimize. But somehow if we convert them in sort of products, then that can also be a better solution. So we can look for developing certain sustainable structural elements also. Like here you can see this pervious concrete. So like why this is sustainable is because if now you might have seen again, read through a lot of literature, what has happened nowadays that in the cities particularly, there are a lot of paver blocks which have been put, and the water is not able to effectively percolate in the ground. So that is one of the issues, and it's otherwise causing flooding also at other places. That is another issue. And of course, we cannot go away with the use of paver blocks, particularly because it provides a comfort to the pedestrians, particularly in case of cities and towns. So we need to look for a certain solution where we can use the paver blocks also, and which doesn't have a negative effect on, you can say, sort of a environment, and there's a water recharge also. So people have worked on this pervious concrete, which can be used as a paver in pavers, and where water can percolate through this easily. Of course, there are certain issues associated with this. That one of the issues is that these pores, they get clogged with the time. So we need to work on different aspects, and that's also an interesting research area where we can work upon, we can find out, we can think of developing certain solutions where the concrete is pervious, as well as where the clogging problem is not there. I know a couple of research groups who are working on this. Of course, our research group is also working on this, finding out some solution where we can have a balance of recharge of water, as well as uh, not the clogging or recharge of water, including prevention of clogging in the concrete. So this is what you can work upon, and you can develop certain different types of products. Another interesting like sustainable structural element which I just need to show here, of course, in one of the lectures, Dr. Vivek will be discussing that in detail. Like this is just an example how we can work for the society. We can come up with some interesting solutions. So this is a typical colored bilayered bricks. So what happens nowadays is because of these sustainability concerns, people are now going for the fly ash bricks. But the problem with our that if you see the societal aspect again that comes into the picture, we do have a tendency to go for red colored bricks because we consider that red color as auspicious, and the fly ash bricks they don't have that color. So many times there are no takers for fly ash bricks. Otherwise, also if you are going for fly ash bricks, then you need to go for this plastering, or you need to go for paint, etc., to give it some aesthetic look. Otherwise, that's not that much aesthetic. So we try to find out a solution where we can make these bricks as, aesthetically pleasing, and by using certain waste material. So here, like we try to use the waste stone dust, which is available, colored stone dust, and we try to put one layer of that colored stone dust over in the brick in the manufacturing process only. So here what's happening is there's a top layer which is made of waste material, colored waste material. So the advantage with this type of brick is it is like sort of giving the color also, aesthetic appearance also. It is utilizing the waste also, and it is reducing the cost also, because otherwise you have to go for paint, etc. So it reduces the cost also. The complete details will be shared by Dr. Vivek. So such type of sustainable structural elements we should work upon, and this because this will be really beneficial to the society, which will be a like sort of direct application to the society. So, however, this is not as simple as being shown, and when we are developing or using sustainable structural elements, we require application of engineering, and we need to see the specific purpose also, and we need to optimize different aspects also. We need to see its durability aspects also. Now, how then another aspect about this sustainability is we have to look in the long term also. That is, we have to make the durable structures. And what are durable structures are those structures which last longer and which require lesser cost on operations and maintenance. And thus, for ensuring a good service life of the structure, durability is an important aspect. And there are different forms of durability like water permeability, carbonation, freeze thaw, corrosion, abrasion, and alkali silica reaction, then acid attack, and so many type of durability parameters are there which we need to look into. And the advantage why we need to improve the durability is because it has its own certain advantages, like it improves the life cycle values. The durable structures, on one hand, they will increase the utilization period of any structure, and on the other hand, they will improve its scrap value also, resulting in a better life cycle assessment, or rather life cycle cost. It also gives reduced operation and maintenance. With improved durability, structures are less likely to suffer damage in the long run. And it also gives a safer construction, because this leads to this results in a more safer and more safe and more reliable concrete structures. And another aspect is we need to adopt latest technologies also when we are talking about the sustainable construction techniques to understand what's happening actually when we are making certain changes in the materials. So what is happening at the microstructure level also. So there's a utilization, or rather there's a requirement of these techniques, latest technologies also, like microstructure analysis, mineral characterization, pozzolanic strength index. In microstructure, you can see actually what is happening inside the concrete at that microstructure level. Like here, I have just picked up two examples. Like here, we try to use ceramic waste as replacement of fine aggregate in the concrete, and then we try to use this NMR technique, which is mostly used by chemistry background persons. And by that NMR technique, we can find out the degree of hydration. So you can see that in the conventional concrete, the degree of hydration was 48%. When we use ceramic waste, the degree of hydration went up to 73%. The bond chain length also increased in the ceramic waste concrete. So by using this NMR technique, this gave us a confidence that yes, the degree of hydration is increasing, the bond length chain is increasing when we are using ceramic waste. So that's a win-win situation, that we are able to replace the natural material by a waste material, as well as we are able to get a good degree of hydration and a good bond chain length. So these techniques also we need to learn when we are talking about the sustainable construction practices. When we are going to introduce some new material, we need to work upon them. Like here, a very latest technique, LFM, a lateral force microscopy was used, and here we are seeing that in the traditional concrete, there's a non-homogeneous phase. In the concrete which is containing 40% ceramic waste, there's a homogeneous phase. And in the traditional concrete, there's high variation in distribution of phase. In the concrete which is containing 40% ceramic waste, there is a relative smooth distribution of phase. So again, this lateral force microscopy technique, this has been used conventionally by people from the physics background and those who have been working on very smooth material like metals, etc. But as a construction engineer, as a civil engineer, or those who are working in this particular domain, we need to now look for those applications also. We need to go up to that level of precision, because it has happened that conventionally people have seen the concrete as a very vague material or as a very raw material without going much in the detail. But actually, it so happens that whatever is manifested at the physical level, that whatever strength we are getting, whatever durability we are getting at the physical level when we are testing the cubes, so when we are doing it at a macro level, actually that's a manifestation of the microstructure of the concrete. So we need to go deep into the microstructure of the concrete if we are willing to really establish the application of new material or the application of new technique for the benefit of the society. So the idea of showing these two slides is, yes, we should be quite open. And conventionally, we do have, when we talk about the sustainable construction materials, we have a tendency that we just replace some material by some waste material, and we do the conventional, that sort of compressive strength testing, flexural strength testing, and then a bit of durability test. But that is not sufficient. As engineer, we need to actually see at the microstructure level what's happening. Only then we'll be able to relate actually what is happening. We'll be able to identify the optimum percentage levels, replacement levels. Otherwise, more or less, it will be just a broad guess only that we are getting improvement in the strength, we are getting improvement in flexural strength, but decrement in the compressive and this compressive strength. One strength is improving, other strength is decreasing. Some durability parameters are improving, some durability parameters they are getting adversely affected. If we really want to see in totality, we need to adopt these latest technologies also. So that was from the material perspective. Now, if we talk about the planning perspective, another important aspect at the broader level is efficient design and planning also. So a well-designed building has good natural light, proper air circulation, and thermal resistance, among other things. This ensures that the building is less dependent on artificial sources and more on natural sources, thus providing an energy efficiency. So the advantages of efficient design and planning is the building will have a low carbon footprint. So well-designed structures well-designed structure will always show lower carbon footprint in terms of CO2 emission and energy use. It will also show it will also show better noise control, and therefore it will limit the noise pollution. And well-designed structure have better sunlight and do not require energy for the same. Of course, we do have two lectures by two experts on this area also, from Mr. Vyas and Professor Garg from IIIT Hyderabad. We're talking about this life cycle assessment part also. Life cycle assessment is, as we have discussed earlier, it's a technique to assess the environmental impacts which are associated with all the stages of product's life, from raw material extraction to processing to utilization up till end of life. It's also said that it's a cradle to grave approach. So means from the very beginning to the very last, what is overall environmental impact that we need to see in totality. It's not only about just one component, like we need to see the resources from where it is picked, then manufacturing, distribution, its use, and how we are disposing it off. Even if we are disposing it off on land and we are not able to dispose it properly without landfill disposal, then also that's a big problem, and that will add to the life cycle costing. So, but to do this life cycle cost, we need to have the data at various stages. And in Western countries, now there are standard documents available there for each activity. They have the equivalent CO2 means listed against each activity. And in our country also, people are working on that aspect. Some research groups and some government agencies are working on that aspect, because that is very much essential to obtain the life cycle assessment. Otherwise, more or less, it's a broad guess only. So that has to be codified at a uniform level, that how much CO2 is likely to be emitted for one activity. So those standard guidelines, they are the need of the hour. And that's also another area where those who wish to take up the research career, or who wish to carry out the research in new domain, they can take up this area, because that's quite an interesting area, and which will have very huge implications or very huge applications, in fact, in future. So significance is that it's a quantification tool used for assessment of any material, product, or sustainable practice. It gives a comparative analysis between two or more construction activities, not essentially in terms of money only, but in terms of its impact on the environment. And it gives a perspective on their sustainability also. So examples of sustainable construction practices we can see, like we can use PPC and PSC as blended cement. We can use fly ash bricks instead of conventional clay bricks. We can use artificial aggregates. We can use recycled aggregates. We can use sludge as binders. We can use mine tailing as aggregates. Then Griha rating. Griha rating is like a rating which is now being given to the buildings, and complete guidelines given by the government of India. So there are certain certified professionals who work on this Griha rating. You can get your building certified on that Griha rating. And LEED also is some type of rating. Mr. Vyas is an expert who will be talking about these aspects. Maybe I think tomorrow or some day he has one lecture on this. And another important aspect is, like, if you really need to optimize this entire construction activity, then we need to go for this latest technology of building information modeling. So building information modeling is that technique where we just codify everything, all the activities of the construction in sort of a data, or we can work upon, and we can see the linkages of different construction activities. And if we have a very good building information modeling system for our structure, we can save a lot in terms of time, as well as in terms of money, as well as in terms of resources. So we do have a lecture on this building information modeling also from one of the experts from LICMARC Pune. Now, if you see certain concepts which are conventionally associated to sustainability are, like, one is waste hierarchy, another is circular economy, carbon footprint, 6R concept. These are some concepts which people have been talking. So as an engineer, we should have some brief idea about these concepts. Of course, some of the concepts you might be knowing earlier also. So one is waste hierarchy, and that's quite important. Waste hierarchy. What is waste hierarchy? Is we need to see the manner in which we need to tackle the waste. What is the hierarchy for that? So the hierarchy is, if you see on the right hand side, the hierarchy is, first is the least favored option is landfill. And then another is recovery, or if we start from the top, the most favored option is reduce. That why don't you reduce the use of the material? So that is the top hierarchy. If we are able to reduce the use of material, That is the best. Then if you're not able to reduce the use of the material, then at least we should reuse the material. That's the next. And even if we are not able to reuse the material, then at least we should be able to recycle the material. And when we are not able to reduce the consumption, we are not able to go for the reuse of the material, we are not able to recycle the material, then at least we should look for recovering the energy from the waste. And when we are not even able to go for reduction in the consumption, then and we are not able to go for reuse, we are not able to have a technique for recycling, we don't have a technique for recovering the energy from the waste, then the least favored option is landfill. Now, so this is the hierarchy, and we should, as an engineer, we should focus on the very first, second, or third at least, and we should not go below that. And the time, like reduce, how we can reduce the amount of waste which is produced is we can optimize our designs. So that is reduction. Reuse, we can use such type of materials which can be reused, like steel structures, they can be reused. Recycle, like if you have some concrete structure and if you're demolishing it, then at least we can use the C&D waste. So that's sort of recycling. So we should essentially try to focus on the first 2-3 parts, which are the most first 2-3 options, which are the most favored options. Another concept which is often talked about is circular economy. And it refers to the use of one industrial waste into another while creating new economic paths. So the figure on the right hand side is like representing a circular economy in terms of waste hierarchy. Like there's a building material, then it goes in the construction, in service, in operation. Now after the operation, it can go in the repair. If you're going for the maintenance, it can go here. If you're reusing, it will find its entry here. And if you are refurbishing or recycling, it will find its entry here. So it is how much we are able to sort of go in the circular economy. But each material, it can, in that hierarchy, it can go back to some earlier sequence and it can again come in this economy. So we can go for repair, we can go for maintenance, we can reuse it, and we can recycle it. So again, it will reach up to this level. Again, we can come here and again, this circle can keep on going. And then we can just have a circular economy for energy recovery also in the landfill also. Another aspect which is being discussed often is the carbon footprint. So the carbon footprint is the indicator of negative impact of any agency or individual on the environment. And it is measured in terms of carbon emission during its entire life. Like clinker manufacturing is an activity with a very heavy carbon footprint. That is the clinker manufacturing, which is a part of cement industry. That's why people are looking for alternatives to the cement or alternative cementitious materials or supplementary cementitious materials. So this carbon footprint is also very essential to work upon. And nowadays, if you go through the literature, if you read the newspapers, then you might have seen recently there was a news on this ranking of the smart cities, and those cities which have worked upon this carbon footprint, they have got better marks or better ranks, because that is one of the components on which government is also giving emphasis. Even in Madhya Pradesh also, when two cities were compared, like Indore and Bhopal, Indore had an edge over Bhopal because Indore has some projects where they have been able to work upon this carbon footprint activity. So this is another important aspect where we need to work upon. And then if you see overall, this another concept of the sustainability in construction is this 6R approach, where the 6R approach is listed like rethink, refuse, reduce, reuse, recycle, and rot. So rethink is whether any construction activity is needed and is it the most sustainable alternative, or is it is the most sustainable alternate available. So first is we should rethink whenever we are going for any construction activity, we should just think before that. So is that really needed? And if it is really needed, that is this the most sustainable alternate? Most sustainable alternate, like there might be 10, 20 different types of constructions which are possible. Then which one is the most, which one is like the most sustainable alternate, that we need to see. Now this includes, like at this level, rethink level, this will include life cycle assessment and including life cycle costing, BIM, building information modeling, and other forms of sustainable assessment and planning, like the use. We can at this level only we can see how it will work from the Griha point of view, from lead point of view, and then we can take an appropriate decision. Of course, it will depend on your geographical locations also and your requirements also. So we cannot 100% codify that. But these are some of the techniques, LCA, BIM, Griha, lead, etc., which will give us some aspect, or which will give us some indication that whether there is some other sustainable alternate available or not. Second, then we should go for refuse. That is, we should refuse the use of natural construction material as much as possible. So we should look for the alternatives of the natural construction material. Of course, we have discussed about a lot of alternatives, like we can use the alternatives as aggregate, also alternative as reinforcing material, also alternative as supplementary cementitious material also. So we should refuse the use of natural construction material. And then third is we should reduce the wastage in the construction, and we should go for overall material consumption through efficient planning. So that is the third aspect. Fourth is reuse. So are we able to reuse the constructed works in construction? Like we can often reuse the steel, we can often reuse wood, and we can reuse similar precast and prefabricated elements in new constructions. So we should look for that aspect, and that's where steel has a little bit of advantage over the concrete structures, because the steel elements, they can be reused. And nowadays there is a talk about demountable structures also, where the entire structure can be demounted. So we should look for those sort of demountable structure also. Is it possible for us to go for demountable structure? And what will be its utility vis-a-vis the conventional concrete structures, vis-a-vis the conventional steel structures? Or shall we go for sort of composite structures? Of course, Professor Mishra will be discussing about a prefabricated structure, where they have an edge in this, because those elements of prefabricated structure, they can be reused. Then next is recycle. Can we recycle any waste or other waste in the construction to lower the environmental impact? So we need to look for that. And the least preferred option is to use it as the landfill and then let the material rot back to its natural state in a long period of time. So these are the different aspects, and these are some of the references which I have picked up on.